Comparative linguistics allows us to use ideas governing human speech to explore animal communication systems. For example, humans gather a lot of information from the voice inflections and the pitch and amplitude changes, even when the words of a sentence remain the same. For example, we can infer things like sex of the speaker, urgency, and whether the sentence is a question or a statement, and can even predict when the person is going to stop speaking, all based on these acoustic characteristics, regardless of the words being spoken. Here's an example of two words being said by people of different sexes and with seemingly different meanings that are only interpreted based on pitch and inflection.
Need help?
Need help!
Bottlenose dolphins have individually distinctive signature whistles. These are characterized by stable frequency-time contours and are known to broadcast the animal's individual identity to conspecifics. Here are two examples of signature whistles of our dolphins. These are depicted as spectrograms, with time in seconds on the x-axis and frequency in kilohertz on the y-axis. The relative amplitude is represented by the brightness scale, with lighter colors representing louder amplitude. You can see and hear the distinctive pattern. The first one is the dolphin on the left, with the blue and green spectrogram. The second is the pink and purple spectrogram. We work at the National Marine Mammal Foundation, where we have an ongoing research project studying the vocal behavior of the U.S. Navy Marine Mammal Program's dolphins. As part of this project, we record the whistle behavior of 8 dolphins while they spend time in above-ground pools as part of their mobility training. These animals are habituated to this context, and as you can see in this photo, they oftentimes have pools very close to them with another animal in it that they are able to communicate back and forth with. A vocal catalog is maintained for each dolphin, and the signature whistle has been confirmed by multiple observers as the most commonly recorded whistle type emitted when that dolphin is separated from conspecifics. Signature whistles have a very consistent frequency-time contour. Here is an example of 50 iterations of the same dolphin's signature whistle plotted on top of each other, but standardized in terms of time on the x-axis, with peak frequency on the y-axis. You can see the consistency between these contours. What we really do not understand yet are if the amplitude modulations across whistle contours are also this stereotyped. And if not, are amplitude modulations related to frequency and/or time? We have recorded the dolphins' whistle repertoires over the last 3 years using sound trap hydrophones. Whistles are omnidirectional, which allows us to receive clear recordings of the whistles no matter where the dolphin is in the pool. The maximum distance from the hydrophone a dolphin could be is 7 meters away, and therefore, over the course of a single whistle emission, it is highly unlikely we have large changes in position or orientation. When possible, 50 signature whistles, a minimum of 30, for each animal were chosen. We further extracted acoustic parameters of each whistle using PamGuard open-source software, and the Raka plugin developed by Oswald and colleagues. The output is the frequency and amplitude at every 1.78 milliseconds across the whistle contour. All amplitude measurements were standardized into z-scores to give us relative amplitude modulation over the course of a single whistle in order to control for changes in distance and orientation between different signature whistle emissions. Remember this figure where we depicted this animal's stereotyped frequency-time contour over 50 whistles? When we plot the relative amplitude contours of those same whistles over time, you can see that we have a much less stereotyped pattern. This was consistent across all 8 dolphins. This figure shows the mean correlation coefficients plus or minus 1 standard error of the amplitude contours within each individual, on the left and between dolphins on the right. The different colored bars represents the 8 different dolphins. A general linear mixed model, with individual dolphin included as a random factor, found that the correlation coefficients within a dolphin's repeated signature whistle emissions of the amplitude contour were higher than those of the amplitude contours compared between dolphins. That said, correlation coefficients of less than 0.3 represent a relatively small effect, suggesting that although the coefficients were significantly higher within each animal than between animals, a dolphin's signature whistle's amplitude contours are still not particularly stereotyped. In order to understand why we were finding this significance, we wanted to see if peak frequency was a covariate inflating these coefficients. Log transformed peak frequency, depicted on the x-axis, showed a significant negative relationship with relative amplitude on the y-axis. This relationship suggests that it is likely the stereotypical difference in the frequency time contour that is resulting in the significantly higher correlation coefficient within a dolphin signature whistles compared to between dolphin signature whistles, not necessarily due to an actually stereotyped amplitude contour. The colored lines represent the slope of the peak frequency and the mean standardized amplitude for the signature whistles of each of the individual dolphins. The lines begin and end at that dolphin's minimum and maximum peak frequency. The dotted line represents the omnibus regression line for the 8 dolphins combined. You can clearly see the consistent negative relationship across all 8 animals. One pattern we were noticing was that it appeared that the amplitude seemed to fade in at the start and then fade out at the end of the whistle. A regression using time squared as the predictor variable and amplitude as the dependent variable found a significant quadratic effect of time on amplitude. This figure depicts all of the data compiled into one regression, with the standard error bars depicted at every 1% of the whistle's duration. We wanted to ensure this time standardization wasn't affecting our results, so we also looked at the mean relative amplitude for the initial first 5%, the center 5%, and the final 5% of each whistle's duration. A general linear mixed model found that the initial 5% contained significantly less energy than both the center and final 5%, and that the final 5% was still significantly less than the center 5. This suggests that the majority of the whistle's energy is concentrated to the center of the whistle, regardless of the whistle's shape and/or number of loops. This has led us to 2 main hypotheses for further testing. The first is the mechanism of dolphin whistle production. The nasal apparatus needs to pressurize at the beginning of the whistle and then depressurize at the end of the whistle. From a functional standpoint, similar to human speech, we hypothesize that these patterns that may be a function of the mechanism of production may have evolved to be useful cues for maintaining efficient communication during antiphonal calling. Remember our dolphins from earlier? Here's an example of a bout of antiphonal signature whistle exchanges recorded from these 2 dolphins when they were in adjacent pools. The dolphin on the right will be on the top channel, and the dolphin on the left will be on the bottom channel. We can see how they successfully take turns whistling, even though the dolphin on the top frame has a multi-looped whistle that could arguably be hard to predict at what loop she was going to stop. We suggest that because of the stereotyped frequency patterns and a dolphin's use of multi-looped and multiple iterations of signature whistles, frequency declination is likely not a very useful turn-taking cue, but amplitude declination may be. Together, these findings support the hypothesis that amplitude modulation is a salient and potentially overlooked characteristic of whistles used for communication by bottlenose dolphins. The authors are extremely grateful to the Office of Naval Research for their support of sounds as indicators of health and welfare of the Navy's dolphins. We are also grateful to the U.S. Navy Marine Mammal Program for allowing us to opportunistically record the dolphins in its care. If you have any questions, please feel free to ask now or email me.